Hello, everyone. My name is Arthur. I am a postdoc researcher at the University of Campinas, Brazil. And today I'm here to present classification of binaural audio for sound immersion assessment in TV 3.0 on behalf of my colleague Douglas Abreu and our advisor, Bruno Maziero. First of all, I would like to acknowledge the financial support of the São Paulo Research Foundation and the National Council for Scientific and Technological Development in Brazil. And we would also like to thank Professors Regis Faria and Almir Rosa, both from the University of São Paulo, because without them, this study would not have been possible. So, what is TV 3.0 anyway? The history of television in Brazil began in the 1950s, when all we had was analog, black and white images with monophonic sounds, which then evolved into color broadcast with stereo sound. But the real change came in 2007, when we first had access to digital television, which was made possible by the ISDBT standard, which is a Japanese technology. This was then upgraded and rebranded as the Brazilian Digital Television System. And by recognizing a change of pattern in viewer expectations regarding things like personalized content, immersive experiences, IP and geo-targeted based content, etc., the Forum for the Digital Television System in Brazil envisioned a next generation system, which is called the TV 3.0 project. This project is phased, and in the first phase, there was a call for proposals in which new technologies could submit their solutions to the envisioned architecture of the system. Then there was a phase 2 called testing and evaluation, which involved around 70 researchers, including our very own Douglas Abreu. And after evaluating these candidate technologies, those who were completely compliant with the requirements of the project were recommended to the Brazilian Ministry of Communications for the future implementation of this next generation digital television system. Specifically about audio, these technologies, they were required to deliver channel-based stereo, surround sound, and immersive formats, as well as object-based and higher order ambisonics. The sound immersion assessment was done via Mushra tests with over 1 million ratings, with over 300 listening experts, and across 9 different labs. Of course, this was all done under ITU guidances. And just a little bit about Mushra. It's just like those blind taste tests. There is an anchor sample, which is the one that is being evaluated, but the evaluator is also presented with multiple copies of that anchor, degraded versions. But the catch is that there is a hidden reference, which means that it is an exact copy of the anchor. So the evaluator must evaluate the hidden reference well, if applicable, just as well as it did in the anchor sample. But reproducibility wasn't always possible with this kind of test. As you can see here, these are the official results for the MPEG audio technology, and these 3 different labs, they could not agree on the Mushra scores, even for a same audio format and the same bitrate. So we asked ourselves, could we perhaps find an alternative which is scalable, repeatable, efficient, perhaps a computational way that can be automated? And well, if you thought for a second that we were going to use AI for that, you got that right. For some time now, there is something called machine hearing, which is a field of research that we try to give machines an understanding of sounds as close as possible to the human auditory system. And just in case you don't know that yet, recent research suggests that our brain does not interpret sounds directly from time series data, that is SPL over time, but it rather extracts a kind of feature that looks something like these dancing Atari logos that we are seeing here in the corner. This is a simulation which was done for the guitar intro of Wish You Were Here by Pink Floyd. We're not going to play that for copyright reasons. But the machine hearing approach is quite similar. First, there is a recording, and then we try to extract features. The STFT is quite popular because it yields an image-like representation, which is called a spectrogram. And after doing that, we can resort to a computer vision architecture to classify sounds in the same manner that you would classify images, right? So for our experiment, we had to first obtain our own data set. We used the original source material that was actually used in the evaluation phase of the 3V 3.0 project, which were sourced from Global, Dolby, and MPEG. And we had to simulate how this source material would sound to a dummy or human head. So we used the SADIE2 dataset, which comprises binaural and room impulse responses, and we used the convolutional method to simulate how those source material would sound to a person or a dummy head positioned at the sweet spot of different monitor arrays, and also considering different head movements. These are some examples of the features after extraction. These are the left and right spectrograms. And at the bottom there, we have the phase difference between the two ears. And we decided to go for the VGG16 architecture, which comprises 13 convolutional layers and 3 fully connected ones for classification. We used SGD and categorical cross entropy for the convolutional layers, and we used ReLU and L2 penalties for the fully connected ones. We also used techniques such as dropout, early stopping, and patience. And as you can see here by our results, the accuracy in the training and validation phase was quite high, reaching over 90% accuracy, which is good, right? So we had to test this under real-world conditions. This is a controlled environment, which is a room in our lab. This array here comprises a top layer, a bed layer. We have a subwoofer there in the corner. This is the artificial head, and these are the room configurations. The thing here was that we could play mono sounds from the front speaker, stereo sounds using the side speakers, and by adding the whole bed layer, we had a 5.1 surround sound system, and by adding the top layer, we had a 5.1 plus 4 height channels, which is considered an immersive format. And the predictions using that setup were quite bad. As you can see here, the predictions heavily favored the immersive format. These are all confusion matrices, but even for other metrics, you can see here that the accuracy got quite low, 41% in the best case scenario and 18% in the worst case scenario, which is why we decided not to look very much at these. But you may be thinking, well, what happened then, right? So after some investigation, we looked on the original samples that we decided to use for our study, and they vary significantly in length. And also, for inputs to the CNN model, we had to segment them. We chose 5 seconds, so the immersive format had way more samples than any other class in our data set, which causes class imbalance. So just to summarize what we did, Our training data was synthetically produced. We used impulse responses under 300 milliseconds of reverberation time. And despite there was no overfitting, our validation got quite high, which surpassed 90%, but in the real-world setting, this accuracy dropped to 41% in the best-case scenario. The room was a controlled environment with RT under 250 milliseconds, but yet our predictions heavily favored the immersive format, which is kind of explained by the class imbalance that was evinced. Our future work then should tackle this class imbalance and fine-tune the model on real-world data. We can also resort to techniques such as data augmentation to level the number of samples in each class. And we can also consider some class-weighted loss function, and also go for adding other noise models such as the mic responses, etc. So to answer our posed question, human evaluation is still gold for now. And for listening, thank you. And if you have any inquiries after this, you have our contact emails here.